Good afternoon. MEEN415 heat flow lab. This is the video for the lab number 3. Okay, so you so far did 2 labs about for the refrigeration cycle, refrigeration unit. The first one is for the overall knowledge of the refrigeration system, pH diagram, TS diagram, those kind of things, right? The second lab, we focus on the condenser. Okay, we look at the heat balance on the condenser. So the overall loss of heat in the refrigerant will be the overall gain of the heat in the water side, right? It's a heat exchanger. So based on the balance, we can calculate the mass flow rate and the refrigeration system, okay, as well as some other performance criteria. Okay, so this third lab, we will focus on the evaporator. So it's the opposite side of the system, right? It also has heat transfer. Now, the heat transfer is from the ambient air to the refrigerant. Refrigerant is cooler, right? So you have basically that's a heat transfer to cool the environment. Okay, so I probably don't need to repeat that video. Previous 2 labs, we have videos basically running the refrigeration system, pretty noisy, and we do some measurements. Okay, now you are familiar with the system and operation, so I don't have to show you that refrigeration system again. So let me just explain to you the theory of this lab, the heat balance in the evaporator. Okay, then let me give you the data I measured. Okay, so you can do your calculation. Okay, first of all, let me switch my window to the handouts. They're the new handout, lab 3 handouts. I will post them in Moodle. Okay, let me share the screen. Okay, here it is. This is the handout. So this is the number 3 experiment for the refrigeration unit. Okay, so the objective is to study the transient behavior of the heat transfer around the evaporator and to verify heat balance between the refrigerant side and the air side. Now, instead of in the condenser last experiment is between the refrigerant and the water, right? The heat balance. Now, this time in the evaporator, the heat balance will be between the refrigerant and the air. Okay, so again, that's it, the heat transfer, heat balance, right? So the total energy change in the refrigerant side will be equivalent to the total energy change in the air side. Okay, so in the air side, we lose energy, right? Decrease the temperature, so heat loss. Okay, so in the in the evaporator side, the refrigerant receive heat from the ambient, right? So that's amount of energy change will be the same. The heat loss in the air side will be the heat gain in the refrigerant side. Okay, we previously talked about the process in the evaporator, right? You did the pH diagram, you know what is the process in the evaporator. The refrigerant is changing phase, right? From the mixture to the vapor, okay? So the driving force is the heat it received, okay, from the ambient. So it changes phase. So I guess now you know this process is totally heat transfer, just like similar to the condenser, right? Total heat transfer. So refrigerant is changing phase. So does the temperature change before and after the evaporator? So in that sense, if it doesn't change, right, it's changing phase. Of course, temperature doesn't change. It's just phase change. Okay, temperature should be the same. So in the actual measurement, you only need to measure one temperature, right? So in the actual measurement, we measure the outlet, evaporated outlet temperature. The inlet temperature should be the same. Okay, how about pressure? It's changing phase, okay? It's changing phase, so the pressure doesn't change either. It's just heat transfer, of course. Pressure doesn't change. So the pressure, you know the pH diagram you did, right? So it's a horizontal line between the 2 points before and after the evaporator. Okay, so pressure doesn't change either. Okay, so how do you calculate the energy change before and after the evaporator? It's m dot mass flow rate times delta H, right? So you know how to get the delta H, and you know how to get both H's before and after the evaporator based on the temperature and the pressure, okay? So you can easily calculate the, how about the mass flow rate? Mass flow rate, just use the mass flow rate you calculated from the lab number 2. Okay, so you should be able to find the energy change, which is the heat gain, okay, in the refrigerant side. So that will be equal to the heat loss in the air side. Okay, so in this experiment, we're gonna measure the ambient temperature, which has you have a cold box around the evaporator. So it's simulated a small ambient environment. There is ambient temperature. So in the cold box is measured. And the evaporator surface temperature, you can just use the evaporator refrigerant temperature, okay, to use as a surface temperature of the evaporator. So there will be heat transfer, convection heat transfer between the evaporator and the ambient air. Okay, it's convection heat transfer, right? You know the equation. Q equals to HA delta T. Okay, you have the 2 temperature. One is the refrigeration temperature. One is the ambient temperature. You have the delta T. Okay, so you don't know the area. Okay, so you don't know the area, but we can use the thermal resistance. Remember, Q equal to delta T divided by thermal resistance, right? Okay, so you use the thermal resistance. In that sense, now you have the Q, you have the delta T. In this lab, you will be asked to calculate the thermal resistance of the air, okay? Well, since there's a fan there, it's not really the still air, right? It's not convection heat transfer coefficient of the still air. You have the movement of the air. So you don't really know what is the heat transfer coefficient. You can calculate it based on this. I don't know the surface area of the evaporator, so let's use the thermal resistance instead, okay? So that's the main calculation for any instance, okay? You should know every information about for the refrigerant side, okay? You know all the information, so you can calculate the heat gain in the refrigeration side, okay? They are equal to the heat loss in the air side. Heat loss is the delta T divided by thermal resistance, okay? So thermal resistance is the only unknown in the equation, so you should be able to calculate, okay? So in this lab, the other purpose is to investigate the transient behavior of the heat transfer around the evaporator. Okay, so it is a transient process for the cold box. You see, think about the cold box before the fan kick on, before the evaporator start the heat transfer, the cold box has a ambient room temperature, right? Then when the fan kick on and the heat transfer starts, and it's a changing process for cooling this cold box. Okay, it's a transient process. So I think this is the only lab here we will study the transient behavior. So in that sense, I measured the temperatures, pressures, and temperature and the pressures in the refrigerant, right? But also temperatures the changing temperatures in the air side. Okay, so I think it's 30 seconds for the time interval. So every 30 seconds, I read a temperature and read all the information every 30 seconds. Okay, read temperature, pressure. That's why in the actual, when you do the lab, we need 4 people to do this lab, right? It's 1, 2, 3 at the same time. Everybody read different values, so we can study the transient behavior. So but I have the data. I will give the data. So there will be 6 data. Okay, so every 30 seconds, 1 data set. So that will be what, total 3 minutes measurement time. Okay, let me show you what the data look like. Okay, let me turn on the data file. Okay, let me stop share this. Share my data file. Okay. Okay, this is the data file will post on Moodle. Okay, so look at this. There are the 6 readings, 1, 2, 3, 4, 5, 6. The number 1 reading is at the beginning. Okay, number 2 reading is at 30 seconds. Number 3 is 1 minute. Number 4 is at 1 minute and 30 seconds. 5 is 2 minutes. So 6 is 2 minutes and 30 seconds. So total 2.5 minutes measurement time. Okay, so look at this. The temperature, see that the cold box temperature, it changes a little bit, not much, right? So, but it shows the changing. Okay, then the ambient temperature actually is it's not changing. This is just ambient outside the cold box. Okay, so I think this data we measured, it's not from the beginning. So it seems like it starts from 55 degrees already. Okay, get low a little bit, again get higher. So it's supposed to be start from 71. Okay, and then gradually decrease. But okay, but that doesn't matter. That's what we have. The data, that's what we have. Based on this data, you can still look at a little bit transient behavior. So for the evaporators, it does change a lot. So evaporator temperature from 22 Fahrenheit in the first measurement, then it gradually increased to 47 at the end of the 2.5 minutes. That tells you that's actually getting heat, right? It's the whole system getting heat. It increased a little bit, okay? Okay, notice, although the temperature change, it doesn't mean that it's evaporator inlet and evaporator outlet has different temperature. No, it's the same temperature. If you change it to evaporator outlet to become 47, the inlet is also 47. So basically it's changing all the time. Okay, so based on the temperature difference, although this measurement data is not perfect, but it's okay. We can still calculate the heat transfer coefficient, thermal resistance, okay? Knowing what is the Q, right? The Q is from the refrigerant side, okay? In the refrigerant side, see you have the, you don't need the condenser. You have the evaporator inlet and outlet pressure, they're the same, right? See, 10 psig. Evaporator inlet and outlet temperature is also the same, okay? So you should, but the phases are different, right? So you should be able to get your delta H, okay, between the 2 points. Then you can calculate your total energy, total heat gain, okay? So that's the imbalance. Then I think you can actually plot, you know, how the temperature change with time, how the thermal resistance change with time, how the total heat transfer rate change with time, okay? So that's the goal of the experiment. Let's go back to the handout. Let's look at the requirements. Okay, here it is, the handout again. Okay, I think there's no new equation here. I know all the equations, you know it. You already did in the previous 2 labs. Okay, so basically now I just apply to the evaporator side. So the outcome and the reporting here. So first of all, plot the time history of the surface temperature of the evaporator. You have the data, just go ahead and plot it, easy. Plot time history of the air side temperature. Okay, so you please make these 2 plots in the 2 curves in the same plot. Then you can compare air side and the evaporator side. Air side is a higher temperature, right? So place the 2 plots together, two curves together, so show the difference. Then, based on the data, you should be able to calculate the heat transfer coefficient. Oh, no, I'm sorry, heat transfer rate, total energy change, right? Heat transfer rate. Okay, so at any given moment, you have 6 instances, so you have 6 heat transfer rates. Okay, at each instance, and also the thermal resistance of the air. So number 3, put it into 2 separate plots. Okay, 1 and 2, put them in the same plot because they are both of them are temperatures, so you can compare. But for the number 3, the plot for the heat transfer rate, 1 plot, and the plot for the thermal resistance of air versus time, another plot. Okay, so that shows the transient behavior of the heat transfer. Okay. So I guess that's what I want to talk about for the lab 3. You should have enough information to do the report and to do the calculation. Okay. So I will post this handout on Moodle, and I also post the data sheet on Moodle. Okay. So you can start do the calculation in the report. Okay. Let's make the due date not next Monday, the Monday for the following week. I give you maybe about 9-10 days to do it. Okay, since we have posted this not on Mondays, this is Wednesday I posted. So I think Wednesday is the 3rd. So let's make the due date 15th, March 15th, Monday, March 15th. Okay. Okay, I guess that's it. Let me know if you have any questions. Okay.